Hello everyone, welcome back. In the previous videos we talked about linear density. We explained how we find linear density. Now for today we're talking about a term, family of directions. What do you mean by family of direction, and what is the relation between those directions? Now I'm gonna draw some directions here. Let's say we'll go for 0, 1, 1, and another direction 1, 0, 1. Another direction will be 1, 1, 0. Let's have another direction minus 1, 1, 0. I think I will leave the minus 1 for later. For now, let's have this 3. Now, assuming this is the origin, x-axis, that's gonna be y-axis, and this will be z-axis. We said that in order to draw, we will assume that the tails are at origin. So every direction's tail will be at origin. Then those will be the coordinate for the head. So 0, 1, 1, 0 in x, 1 in y, 1 in z. That's the coordinate of 0, 1, 1. So when we're drawing the direction, this direction will be from here till here. Then if I do the other one, 1, 0, 1, 1 in x, 0 in y, 1 in z, that's going to be the coordinate here. This is 1, 0, 1. The direction will come in this manner. Now if I go 1, 1, 0, 1 in x, 1 in y, 0 in z, that's going to be the point here by itself, 1, 1, 0. So if you draw the direction, bring it from origin to that point. Now we have 3 directions in this cube, and let's assume that we trying to find it for FCC crystal structure. Now we said we need the location of atoms, here. Since we have FCC, so we know that there is at each corner there is an atom, and we know that at the face there will be one here. This is at the other face, the center. This is also have one. There's one in the center. Now if we draw the atoms here, since we know it's FCC crystal structure, the diagonal face atoms are touching each other. We know that when we draw those, we have to draw them in the manner that the circles come beside each other. So it will be one, somehow closer, if I can. So make them bigger. I cannot draw a perfect circle. I'll try my best. So the 3 atoms will be drawn in any direction you look at them. For example, if it is you're looking at 0, 1, 1, the other one is the same thing. Why? Because all of them are the face diagonal, and we know that in in FCC face diagonal, the atoms are touching each other. So the direction that we have is stuff from center to center, center to center, and the third one as well, it's exactly similar. What are the atoms? Now we know that in FCC crystal structure, the length of this direction is 4r because its face. The same thing here is 4r. The same thing here is 4r. So the length of all of those three directions, all of them, their length is 4r. Well, finding the number of atoms, we said that we'll take half of the first one, half of the last one, so there will be half here, and one in the middle. That's gonna give us, so 2 half, one in the middle. Let's write it like this: 2 half plus one in the middle. That's going to be 2 atoms. 2 atoms over 4r, which we get linear density for the 3 direction, all of them. So linear density for all of them equal to 2 over 4r will be 1 over 2r. 1 over 2r. Now you realize that there are different directions, but yet they have the same linear density. So we call those directions family. So family of direction is a definition. We're giving it to a set of direction that they have the same linear density. If you have a direction and its linear density is equal to another direction for the same crystal structure, remember, for the same crystal structure, you cannot say that 0, 1, 1, it's a member of a family 0, 1, 1 for BCC, because this is for FCC. You're only comparing with FCC. So 0, 1, 1, it's a member of a family member with 1, 0, 1, 1, 1, 0, and many more. We have it. So the idea of family members, the arrangement of atom in crystal structure, some directions are similar, and they will give you the same linear density. So we call them family of members. So you realize that we may have many other family members here. Any other family members? If I just show it to you, if I take this diagonal here, let's say if I take this diagonal, it's going to be the same, yes? Why? Because the length is going to be 4r. We already know that there is an atom here. There will be one here. Right? There will be one here, and it's one in the middle. So this also will come exactly the same as this. Imagine we have many more diagonals, the top 2, the other side 2, here 2. So how we know that the rest of the family members? How do we know the rest of the family member? It's very easy. It's just a combination of what? 2, 1, 2 number 1, 1, 0. Look at here, 2 number 1, 1, 0. 2 number 1, 1, 0. Even we can say it minus. Minus 1, 1, 0 is still a family member. The minus just simply indicating different direction, but it's still gonna be the same. So you realize that if you have a combination between minus 1, 1, 0, 3 number, minus 1, 1, 0, in a way that there will be 2, 1, 1, 0. 2, 1, 1, 0. Right here, 2, 1, 1, 0. 2, 1, 1, 0. 2, 1, 1, 0. 2, 1, 1, 0. The minus doesn't matter. So I can find many more family members that have similar linear density. I say minus 1, minus 1, or minus 1, 0, minus 1. Still the same family. Why? Because 2, 1, 1, 0. And then you can go combination between them, minus 1, minus 1, 0. So minus 1, minus 1, 0, and you can continue the rest of them. So when we say family member, the arrangement or the Miller indices, as there are set of combination. For example, 2, 1, 1, 0, 2, 1, 1, 0. Minus also is considered, so 2, 1, 1, 0 again, 2, 1, 1, 0, 2, 1, 1, 0. The minus is only indication of, for example, minus, if positive is going north, minus is going south. So that's not going to be a problem. The minus is not going to be a problem. Still have similar. Let's do one minus as well. Let's say I'm gonna clear this board. I'm gonna do minus, for example, minus 1, 1, 0. I'll do minus 1, 1, 0. So let's see that. I'm gonna do minus 1, 1, 0. Now let's assume origin somewhere accordingly, because we have minus 1 for x. I'm going to assume here to be the origin. Wow. Minus 1, 1, 0. Minus 1 in, because this is x, this is y, this is z. We have minus 1 in x, this is minus 1 in x, 1 in y, 0 in z. This is the point that we're looking at, which is minus 1, 1, 0. Then we're drawing the direction. We'll start from origin. Wow, it is still the phase diagonal, and we know that it's FCC will have the same thing. Remember, we call them the same crystal structure, FCC. That's going to be exactly the same. 3 atoms, because they are phase, the length was going to be 4r. The length going to be 4r. And the number of atoms are going to be 2 atoms, the way that we did. So it's still the same way. The length is going to be 4r. When you find the linear density, is going to be linear density. So when we provide linear density as a 1, 1 minus 1, 1, 0, it's going to be again 1 over 2r. 1 over 2r. So how do we present family of directions? We present them in this manner. So we can say that linear density of, we use this angle bracket, we'll say 1, 1, 0. All of them, they have the same density, which is 1 over 2r. This is how we represent linear density of a family. So when you say 1, 1, 0, all of them they have the same density. I mean, this is a family of directions that combine between 2, 1, 1, 0. The 1 can be minus, doesn't matter. We're representing this one, a 1, 1, 0 family member. Thanks for watching.